Hello, y'all. Welcome to lesson 118 of my DP chemistry curriculum. Today we're going over structure 3.2.3 and 4. We will be discussing how homologous series is a family of compounds in which successive members differ by a common structural unit. Typically, it's CH2. Each homologous series can be described by a general formula. We'll learn some of those formulas, but you'll be able to figure them out as well. We'll be able to identify the following homologous series, and it's all the functional groups from the previous video. Furthermore, we'll briefly discuss how successive members of a homologous series show a trend in physical properties. We'll mostly be looking at boiling point here, but we'll also take a look at melting points too. So, with that said, let's just go ahead and do a little reminder from the previous unit or the previous video, which is that classes of organic compounds, those are often based on functional groups. Remembering I'm abbreviating functional group as FG. Furthermore, when we have successive members of functional groups, we call that a homologous series. So one of the most classic examples of this would be the alkanes. So we'll look at some alkanes right now. We have the single carbon alkane. This is methane. We have the following double carbon alkane. You'll notice it does in fact change by one carbon and two hydrogens, like was predicted up here. And this is ethane. Then you can go up to propane, which once again, we add one more carbon and two more hydrogens. So as we look at this homologous series of alkanes, we note that it changes slightly. Furthermore, between all of these, they are the same functional group. They partake in the same homologous series. So we can assume similar properties. Furthermore, we can assume trends in properties. Now, when we're looking at these chemical and physical properties, what we generally have to identify is the type of intermolecular forces. In this case, these are all non-polar, and so we can expect that for our alkanes, these are all going to be London dispersion forces, or LDFs. That's going to be the main force that's governing it. And as we increase in molar mass, increase in molar mass, we can expect an increase in those London dispersion forces. Furthermore, because now we have an increase in London dispersion forces, then we can note an increase in boiling point and also an increase in melting point because they're more stably bonded. They have a stronger stronger attractive force between the molecules because there are more electrons moving around, creating those induced dipoles in London dispersion forces. We're actually going to expand this idea into all of our homologous series. So when we look at IMFs, we know that IMFs determine properties in organics. And there are multiple ways they can do this, but they determine properties in organics by three criteria. So the first is through molar mass. With any homologous series, as we increase the molar mass, we increase LDF. Increase molar mass equals increase LDFs. Now, this could be for any single organic compound. This could be anything in the homologous series of alkanes, alkenes, alkynes, alcohols, aldehydes, ketones, ethers, esters, or ethers, esters, whatever. the more molar mass, the more we're going to have those London dispersion forces. The other one is structure. Structure is kind of weird when you're thinking about intermolecular forces because we generally assume that comes purely based on what makes it up. But we're going to see in just a moment that straight chain can be different than branched chain hydrocarbons or organics. So they're going to have very different intermolecular forces, even though they have the exact same molecular formula. Number three, the last one, is the functional group. The functional group is going to affect polarity. Now, give me just a moment to be a little more consistent here. I was using arrows for it all. It's going to affect polarity, and that means that we can bring in dipole and H bonding into our discussion on intermolecular forces that take place in these compounds. So I'm going to jump back to structure for just a moment with an example. If we look at a 5-carbon chain, something with the formula C5H12, and I'm going to go ahead and use my structural formula, or sorry, skeletal formula. This is a molecule of pentane. However, we could actually bond it where there's a central carbon with 5 carbons bonded around, or 4 carbons bonded around. These two have identical molecular formulas. They are both alkanes. The difference is we have straight chain versus branch chain. But the thing is, when we put multiple of these molecules together, they can actually only get so close physically in the physical space. And so we can actually have molecules closer to each other. And when we talk about any sort of force or electrostatic attraction, one of the biggest factors is that distance between charges. And because molecules can get closer, then we have more surface area and less distance between induced dipoles of London are caused by London dispersion forces. And because of that, then these are therefore we have stronger forces, and then we can also from that assume we have a higher boiling point or higher melting point, less volatility. So we can therefore make inferences about properties. So structure is actually almost just as important as the functional group or the number of carbons, because there are a lot of things that can depend on how close or what orientation those molecules can interact with one another. So that was my little aside on structure. Moving forward, let's go ahead and look at some common homologous series and make some inferences. If we look at the alkenes, or actually, let's start with the alkanes. Alkanes, enes, ines. When we look at those, one thing we generally know is that they're nonpolar. Because they're nonpolar, we know that there is only LDFs. Out of all of our homologous series, these are usually the most volatile. Remember that volatile means that it is more readily going to evaporate, become a gas. When we move on to our aldehydes and ketones, generally what we're going to see is we're going to see that these are polar. So we can start expecting dipole-dipole interactions in these homologous series. After dipole-dipole interactions of our aldehydes and ketones, we can start looking at things like alcohols, carboxyls, carboxylic acids. We can look at amines, amides. And when we start looking at these, less so amides, but we can generally also assume that these are going to be polar and these are going to have hydrogen bonding, meaning that out of all the homologous series, these are going to have some of the strongest intermolecular forces, determining the way that they interact with other molecules. The big thing here is that being able to recognize this allows us to look at homologous series, and we can predict properties based on functional groups. Furthermore, when we start looking at these, not just can we predict their properties based on functional groups, we can also predict molecular formulas. A good example might be the alkenes, alkanes, alkynes as well. Those are always the easy ones to go to. Our alkanes, alkenes, and alkynes. For this, what I'm going to actually do is go scroll all the way back up to our alkanes over here. What we can see is that this is CH4, this is C2H6, this is C3H8. And you may notice that when we bring the carbon up by 1, the hydrogen goes up by 2 from the previous one. These generally follow a very simple formula for alkanes. It's CnH2n plus 2. Now, if we were to remove one of those bonds to make a double bond, so if we were to throw a double bond right here, we would have to get rid of 2 hydrogens to make that double bond work. So for alkenes, we can generally formulate them as CnH2n. And for alkynes, we even have to lose 2 more hydrogens. And so their general formula is going to be CnH2n minus 2. So this is how we can generally predict what these are going to be. When you are adding something like an alcohol, if it's an alcohol from an alkane, it's actually the same formula, H2n plus 2, and an oxygen, because that oxygen is taking the place of one of the hydrogens and still keeping the hydrogen there as a hydroxy group. When you're doing an aldehyde, you are now going to be creating a double bond, meaning you're going to be losing 2 hydrogens, and it actually has a formula of an alkene plus that extra 1. So we can look at like CnH2NO, and this might be an aldehyde or even a ketone. They're both going to be similar in that respect. We're taking away 2 hydrogens and replacing it with an oxygen. So it looks similar to an alkene, but we have an O because we have that double bond. So you should be able to start being able to predict these patterns, but hopefully this provides you a good enough foundation, and have a great day.